So in this particular module, we will learn about basic information on cross electron transfer reactions. We will also learn differences on rate and equilibrium constant for outer sphere reaction and cross reactions. We will also learn Marcus relationship for cross reaction, means how Marcus equation is applied to the cross reactions, and ultimately we will go for the discussion about contribution of various type of free energies on electron transfer. So let us have some kind of introduction briefly about cross reactions. Unlike to the outer sphere and inner sphere redox reactions, cross reactions demand the reacting partners which are oxidant and reductant. Now this case they are different from each other by more than oxidation state. Till now we have been studying on the redox reactions that there are two counterparts. One is having one oxidation state, another is having different oxidation state, and then the electron transfer has taken place. One is oxidant, another is reductant. So this is not the way in this case, exactly not the way. In this case, these two redox partners are different from each other more than the oxidation state. The very common example chosen from numerous known reactions of this kind is reduction of permanganate by iodide anion to afford I2 and MnO4 2 negative. Means MnO4 2 negative means MnO4 negative has been reduced and iodine has been oxidized. As far as cross reactions in metal complexes are concerned, it requires one of the reacting complexes to be relatively inert with respect to the other complex. It is deeply associated with self-exchange reactions that we have already discussed, with the distinctions that cross reaction involves two different metals. In general, the scheme shows MLN(X+) plus M'(Ln)(Y+). Means metals are different for the cross reaction, whether ligands could be same or the metal could be same and ligands could be different, and this leads to the formation of MLN(Y+) and M'(Ln)(X+). So the X goes to Y and the Y goes to X. Moreover, the complex which is relatively inert in nature should not have a binding site. Means non-binding electron pair should be absent, otherwise it will react with the labile partner, and the reaction is like that, cross reaction. Suppose we are taking one part is chromium hexa-aqua complex, which is well known right from the outer sphere inner sphere reactions. You know, it is a labile complex. It is reacting with hexa ammonia ruthenium 3 positive complex. So in this case, one part is what? Chromium hexa-aqua complex, another is ruthenium hexa-amine complex. There is no bridging ligand, nothing like that. So both the cases are different from the outer and from the inner. In the outer sphere, both the complexes are for the same metal and almost same ligand. They are differing by just the oxidation number. In the inner sphere, one of the complex is having labile ligand or the ligand that is capable of bridging between two centers. But in this case, one is labile complex, that is well known, chromium hexa-aqua, and one is inert D6, that is Ru hexamine 3 positive. After electron transfer, they lead to the formation of chromium 3 plus water complex and ruthenium 2 plus amine complex. Although if you see, chromium is getting stabilized by forming chromium 3 species, however ruthenium is going to be destabilized as D6 systems are seldom go for D5 configuration, especially for the D4 and D5 series. So the rate of this reaction is K21 given is equal to 2 into 10 to the power 2 mole inverse second inverse. Although replacing chromium 2 by vanadium 2, remember chromium 2 is D4 while vanadium 3 is D3, from this reaction now provided is what? A cross reaction that contains chromium hexa water 2 plus complex with ruthenium hexaamine 3 positive complex. If you see, both the complexes are labile. It is well known that chromium hexa water 2 plus complex is a D4 system and it is labile, and this case ruthenium is attached with the bit stronger ligands, that is ammonia, and it is 3 plus, so it is basically D5 in configuration, and it is highly needy of getting 1 electron to complete a D6 configuration. So it finally occurs that chromium is going to be stabilized by converting chromium 2 to chromium 3, that is D3, and of course ruthenium 3 plus, that is D5, is getting 1 electron and it is converted to the ruthenium 2 and it is D6. Now this reaction proceeds through the rate K21 is equal to 2 into 10 to the power 2 mole inverse second inverse. On the other hand, if we replace chromium 2 by vanadium 2, remember chromium 2 is D4 configuration while vanadium 2 is D3 configuration. So if in the previous reaction change vanadium 2 instead of chromium 2, what will happen? Vanadium hexa water complex is not at all labile like chromium hexa water complex. So now treating one inert complex, that is vanadium hexa water 2 positive complex with the labile ruthenium hexaamine 3 positive D5 configuration complex, and this time the rate of reaction is 1.3 into 10 to the power 3 mole inverse second inverse. If you see, the vanadium has been converted to 3 plus and ruthenium is converted to 2 plus and acquiring D6 configuration. Some other cross reactions are also known like osmium tris bipyridyl system, where osmium is in +2 oxidation state, reacts with when osmium tris bipyridyl system where osmium is in +2 oxidation state reacts with octacynato molybdenum species where molybdenum is in +5 oxidation state, leads to the formation of osmium tris bipyridyl 3 positive and molybdenum CN8 4 negative. So what is happening? Osmium is getting oxidized by 1 and molybdenum is going to be reduced by 1. So it is one electron transfer process, but metals and ligands both are different. So this reaction is categorized as cross reaction. Another example is iron tris phenanthroline 3 positive D5 system plus iron tetracyanide 4 negative where iron is in +2 oxidation state. They react together and form the stable species Fe tris phenanthroline 2 positive D6 configuration, and the unstable species FeCN6 3 minus, means iron is in +3 oxidation state. So +2 species go to +3 and +3 goes to +2. In this case metal ion is similar but the ligands are different. The third example is iridium hexachloride, where iridium is in +4 oxidation state, reacts with iron hexacyanide system where iron is in +2 oxidation state, and then it reduces iridium 4 to iridium 3 and iron 2 to iron 3. The thermodynamic and kinetic data for a couple of self-exchange reactions are compared with the cross reaction data by Marcus-Huss theory. The data for cross reaction lie between two self-exchange counterparts. Determination whether the reaction proceeds through an outer sphere mechanism is also done on the basis of this theory. The equilibrium constant for self-exchange type reactions are given as K11, K22, etc. But for the cross reactions, such constants are given like K12, K21, etc. So K11, K22, K33 and so on. It is for the self-exchange reaction, which clearly indicates that the metal ions and the ligands are same, except the isotope leveling can be done at one of the metal centers, so that we can discriminate what kind of electron transfer reaction is going on. While when you talk about the cross reaction, the metal or ligand both could be different, or metal could be different, or ligand could be different. Likewise, standard Gibbs energy of cross reaction is denoted as delta G 0 1 2, not 1 1 2 2 like that. Delta G 0 2 1, it's like that. For self exchange reaction, delta G 0 equal to 0, whereas for cross reaction, delta G 0, that is actually free enthalpy, does not equal to 0. So what is the change? For self exchange reaction, since the counterparts are changing by the oxidation states only, so that is delta G free enthalpy is 0. For the cross reaction, the delta G does not equal to 0. Gibbs free energy of activation, that is symbolized by delta G hash, is given in the equation like that. Delta G hash, that is free energy of activation, is equal to delta Wg plus delta Sg plus delta Og plus RT ln K T by Hz. Now delta Wg, that is energy related to repulsion of ion in bridging the oxidant and the reductant partners close together. Means the oxidant and reductant species are distant, so the energy required to bring them closer together is denoted by delta Wg hash, while delta 0 G is energy related to the change in the metal-ligand bond lengths. To adjust the metal-ligand bond length needs some energy, and that is denoted by delta Og. The parameter delta S, delta G is related to the solvent rearrangement. Delta S denote for the solvent, so it is the energy required to reorganize the solvent, and T is the temperature in Kelvin, R is the gas constant, K is the well known to everyone, it is Boltzmann constant, H is Planck's constant, Z is effective collision frequency in solution having the value around 10 to the power minus 11 decimeter cube mole inverse second inverse, and ln Kt by H dash accounts for energy lost in the formation of encounter complex. Now when metal oxidant and reductant come closer together and suppose electron transfer take place, they bring and they separate, like formation of precursor complex, then electron transfer process, then formation of successor complex, then dissociation of the successor complex, these things do. But when they come close together, there are three values of change in free enthalpy. It could be 0, means the delta G could be 0, or delta G 0 could be small or negative, or delta G 0 could be large negative. Means if the system, if the electron transfer or the formation of ultimate product is quite feasible, the delta G 0 will be large negative, but if the system is bit favorable, the delta G 0 will be small negative, and if the systems are in equilibrium, the delta G 0 is absolutely 0. So next is Marcus-Cross relation. An equation was illustrated by Ridwell A. Marcus pertaining to the electron transfer as well as for the calculation of associated rate constant. The basic hypothesis behind deriving this equation is the solvation additivity and the vibration barrier that we have discussed in the previous module of the reacting couple. So the reacting couples are having solvation additivity, how much solvent is added to the system, means it is a kind of salvation barrier plus vibration barrier of the reacting couples. So the Marcus equation, which generally express the rate of outer sphere reaction for the electron transfer process relating to the change in free energy, is K12. I remember K12. K12 denotes for the cross reaction, and it is equal to under root K11 into K22 into K12 into F12. So this is the equation. If we are having the values of K11, K22, K12 and F12, we can calculate the overall constant K12. So K is basically equilibrium constant. The capital K denotes for the equilibrium constant, small k are the rate constants for the self-exchange reaction, F is the correction term for the free enthalpy differences between two adducts. K11, K22, K12 and capital K12 can be acquired experimentally. Alternatively, K11 and K22 can be obtained theoretically. So the equation is K equal to chi capital Z E minus delta G dash by RT. So K12 experimental dot E is reduction potential for cells. The parameter F is generally close to 1 and it is given by log F equal to log K12 square by 4 log K1 K2 by Z square, where Z is what? Z is collisional frequency. The most significant equation for one electron transfer process at ambient temperature, that is 25 degrees centigrade, is log K12 Kg small log K12 equal to 0.5 log K11 plus log K22 plus delta E is 0 by 0.059 plus log F. For such cross reactions, one order magnitude to the rate is contributed if delta E 0 increases by 0.12 volt. The cross reaction deviates from outer sphere mechanism and may signify other than outer sphere mechanism is if calculated K12 value obtained from the above equation. It corroborates with the experimental value of K12. The electron transfer barrier comprises two parts. One, that is thermodynamic part G120, and second is intrinsic contribution. The equation that represents activation of free energy for electron transfer is delta G12 is equal to delta G1 dash plus delta G2 by 2 plus delta G12 by 2. So that is intrinsic thermodynamic contribution. It is evident that a bridging ligand that can serve as Lewis base is the one most essential condition for inner sphere mechanism. However, employing ambidentate ligands instead of normal Lewis base ligand, one can differentiate whether ligand attack is proximity or remote. Therefore, two separate mechanisms are known for electron transfer through bridging or sharing ligands. First, one-step mechanism that involves redox reaction between the redox couples only, or two-step mechanisms that involves bridging or sharing ligands in the redox or electron transfer reactions. The activation of electron transfer reactions can be achieved either thermally, wherein lower energy complex is preferred, or photochemically, wherein higher energy complex is preferred. One example that how to calculate the rate constant for the cross reaction is MnO4 minus is reacting with the FeCN6 4 minus. So MnO4 is where magnesium is maximum oxidation stage, is acting as an oxidant, and FeCN6 4 minus, where iron is in +2 oxidation state, is acting as reductant, and they form MnO4 2 negative and FeCN6 3 negative. So the reduction, one electron reduction of MnO4 minus leads to the formation of MnO4 2 minus, and the E0 value for this reaction is 0.56 volt. While reduction of iron 3 species, that is FeCN6 3 negative, is 1 electron reduced and forming Fe2 complex FeCN6 4 negative, and the E0 value for this reaction is 0.36 volt. Now, combination of MnO4 minus plus MnO4 2 minus, that is kind of outer sphere reaction. So the K11 is the rate constant, and it forms MnO4 2 minus and MnO4 minus, and K11 value is 3600 mole inverse second inverse. On the other hand, FeCN6 3 negative plus FeCN6 4 negative, suppose this rate constant is K22, and this forms FeCN6 4 minus plus FeCN6 3 minus, and the K22 value is 300 mole inverse second inverse. Remember, delta G0 equal to minus RT ln K. It is known. Also delta G0 equal to minus NF delta E. Therefore, minus RT ln K equal to minus NF delta E. It is very simple, and K equal to E to the power minus NF delta E0 by RT. So K12 overall is given by K12 equal to E power 38.94, and the difference between the oxidant and reductant, that is 0.56 minus 0.36, that is equal to 2.4 into 10 to the power 3. Overall K12, that is rate constant, not equilibrium constant in this case. So the K12 is equal to 3600 into 300 into 2.4 into 10 to the power 3 under root, that is equal to 5.1 into 10 to the power 4 mole inverse second inverse. So the rate constant experimentally observed is 1.3 into 10 to the power 4 mole inverse second inverse. So this way we can calculate the rate constant by applying this theory. So in summary, the fundamental understanding on cross reaction are obtained from introductory section. The information obtained from equation illustrates how rate of cross reaction can be obtained from self exchange reactions. Further, we have also seen that Marcus cross relationship equation helps to determine rate constant. Contributions of diverse free energies on reorganizations of reactants is discussed, and summation of all free energy gives a total energy of activation for cross reactions.